Hi everyone. So the item on the bench today is this aircraft frequency converter. So let me get this item opened up. Let's have a look around inside and see what it takes to try and power up this frequency converter, see if it still works. If it doesn't work, we'll try and fix it. Now, I don't have any electrical connections or schematics for this frequency converter, so we'll have to take some resistance measurements on these connectors right here on the side panel. I guess you could call this the front of the converter. And this larger connector looks to me like it would have the power in and out, and there's a smaller connector here that might be for control, remote monitoring, possibly even paralleling multiple frequency converters together to increase the total power capability. But we'll start with this connector first and have a look and see what it takes to just get power into the converter and try and power it up that way, and then see what happens. And there's a circuit breaker or power switch right here, but otherwise pretty sparse as far as any other indicators or controls. Now you have to remember that this is meant to be used in aircraft, and this would be in an equipment rack or an equipment bay. Any controls and switches and so forth would be in the cockpit. So the whole purpose of a frequency converter on an aircraft is because standard aircraft power is 400 hertz. And the reason that it's a higher frequency than 50 hertz or 60 hertz, it's commonly used for AC line powered devices around the world, is because when you increase the frequency, the core of a transformer can be made smaller, so less iron in the core. So obviously weight is a concern with aircraft, and by making the core of transformers smaller, power supplies can be smaller and so forth, then that's just less weight. And so 400 hertz is used for the avionics and instrumentation and so forth in an aircraft. Now, you can't take a standard 60 hertz or 50 hertz line powered device and operate it on 400 hertz, because in most cases it won't work correctly. Now, there can be exceptions to that. For an example, a standard incandescent lamp wouldn't care what the frequency is. And there are other types of power supplies that could possibly work on multiple frequencies and wouldn't be an issue. But certainly there are devices that have to work on 60 hertz, and if they're taken on board an aircraft and you want to power them, then you need to use a frequency converter like this. So there's a little data plate on the side right here, and I'll put a larger picture up on the screen. And what this says on the side is 1000 VA, so about a 1000 watt frequency converter, model 4A1001H. There's a serial number. So that the input frequency range is 360 hertz to 440 hertz, so 400 hertz being the standard. Then it says the voltage on the input is 115 or /200 volts RMS three-phase Y. So it's not 115 or 200, it's because it's a three-phase Y connection. That's why that double voltage is listed like that. So you're getting from phase to phase 200 volts, and phase to neutral is going to measure 115. But notice it's three-phase power, so to operate this converter is going to require three-phase 400 hertz. Well, not a problem, because I actually have a power inverter that takes 28 volts and converts it over to three-phase 400 hertz at exactly this same voltage range. I talked about that frequency converter in the video where I gave an overview of the equipment that I use on the workbench. So if you want to see a little bit more details on that power inverter, you can check out that other video. So I really won't go into the details on that inverter, other than it is a Unitron PS65228. All right, so the current here listed at full load says 5 amps AC per phase, and then the output frequency is 60 hertz. Voltage, 115 volts RMS. Of course, it's single phase on the output, not three phase. And then it says power factor, 0.7 lead to 0.7 lag, or 70% lead, 70% lag. Weight, 15.5 pounds. Some other long number right here, I'm not sure, is this catalog number? It looks like it was kind of crossed out, but that's not really important. And it was made by Avionic Instruments Incorporated, and they're still in business. So I don't know year of production, I really don't know anything else about this unit. So that's really the only markings that are on this device. The back right here, there's a cooling fan. You can see the little vent right in there. Like that. The bottom of the unit, nothing exciting going on there, but you can see a lot of screws, and they're all countersunk, recessed, so the panel is flat. And the sort of anodizing that's on the outside is faded a little bit, and you can almost see it looks like fingerprints, in other areas, but it has faded just a little. Maybe this was exposed to sunlight or something over here, or maybe something rubbed against it and kind of changed that dark anodizing that's on the aluminum. But anyway, other than that, it looks like it's in reasonably good shape. I don't see any damage, physically on the outside of the unit. So a lot of screws on the top cover right here. So let me start by getting those removed. Grab the Phillips right here. Most of them are a smaller size, 4 right here that are a little bit larger, but it looks like the top cover is what's needed to get inside. The end cover comes off, but we wouldn't want to start with that. And of course, everything is mounted to that bottom plate. So we'll start with the top cover and see what that reveals when I get this top removed here. All right, let's take a look inside. Oh wow, that looks really nice in there. Very cool. Wow, let me tip that up there. You can see in there a little bit better. Definitely a lot going on. So again, I don't have any schematics for this frequency converter, but obviously a control board up here. Power switching going on over here. Big 3-phase transformer right here. So as I mentioned, input's 3-phase. You can see the 3 windings right there. All right, so let's take a look here at tracing some wires from this connector on the power side over to the input. See exactly how things are connected here. And it looks like to even have a chance of getting to this, we're going to have to remove this board. So again, this is definitely compact in here and pretty tight. So yeah, it doesn't look like there's really going to be any way to get down in there. So let me take a closer look and see what's going to be required to actually get to this connector and underneath this board. Definitely plugs together right here. That's a good thing. Looks like it'll be pretty easy to get this board out as far as disconnecting it. So let me take a closer look and see what needs to be done for a little bit more disassembly. All right, so after removing another handful of screws, I was able to take the side panel off. And with the side panel removed, then this circuit board was able to lift out because it was kind of trapped along this edge right here, and then this connector unplugged. So it gets this out of the way for now. And we can take a look down here. And actually, if I tip this up a little bit, you can see some very large filter capacitors down in there. This heatsink grease, they were using this side panel as a part of the heatsink. But very nice construction, as expected. Anything aircraft related is top quality and definitely built for reliability. You have to remember as well, this is intended for use in high altitudes. I would imagine maybe as much as 50,000 feet, perhaps even more. And at those high altitudes, cooling becomes a concern because the air is thinner. So for this to have the ratings that it is supposed to have in continuous operation, 1,000 VA, the cooling and the design of the electronics has to be such that it can operate at those higher altitudes. And of course, the vibration and the reliability that this has to be subject to, it can't fail under any conditions. So very, very high quality construction and very high quality components. So it looks like probably tracing the input is going to be the easiest to start with, because if you look at this 3-phase transformer right here, you can see there's a green, blue, an orange, and then a black. And you can see this black wire right here, it has the 3-phase windings, so the 3 different windings all joined back together. So that's that common point that would be at the center of the Y configuration. So that's the neutral. And then these are the 3 phases right there. So if I follow these 3 phases back over, the wiring right here just goes right to the circuit breaker. So if I probe from the circuit breaker over to this connector, we ought to be able to trace the input very easily. And then if we can find the output, that would be the next thing. So let me grab my multimeter right here. Go. So I'll just put that in the continuity mode. You can see that, okay, and then you'll hear it beeps when those have continuity on the test leads. So I will turn this on. You know what? I'm going to leave this off, because with this off, that's going to isolate the input from the transformer's windings, and then we won't have any path of resistance through the windings to one of the other phases. So I think just leaving this off for now. What I will do is just go to this one side. It looks like right here. This wiring down inside tip this up again right here. You can see on the back side of the circuit breaker, this wiring right here, again, color-coded with the same colors that go to the transformer. This wiring is looping around and going into the shield, or this box that's right behind this circular connector. So I'll just probe on that side of that circuit breaker. So let's try this. So I'm going to pick these on the connector right here. There's 3 pins in the middle that are larger. I'll pick those to start with. Those might be the inputs. It would kind of seem like maybe they would use those, but... Aha, yes. There's one right there. Let's try... So, now that shouldn't have continuity to the same one, so let's make sure... Nope. Yep, it's over here. Perfect. And let's try this one. Should not be there or there. It's probably the middle one. Yep. What was? It is, yeah. Perfect. Okay, so these 3 large pins in the connector right here are the 3-phase input. Now the common, I don't quite see, that's this black wire. I wonder if that just goes to the chassis. It probably is ground on you know, just a common. So let's try this. Aha. So this smaller pin in the top corner right here has a direct connection. I think it was a direct connection. Let's make sure we have a good connection there. Yeah, perfect. Okay, so there's a direct connection on that pin to ground and not on any of the others. Perfect. So it looks like the 3-phase input is going to be on these 3, so the 3-phase, the hots will be on the 3 middle pins, and the neutral will be on this upper pin right here. So take a note in there. There's probably letters next to those pins. Yes, there is. So A is neutral, D, E, and F are going to be the phases. All right, perfect, easy enough. So now let's see what we can do to find the output. Just the overall design, I think what they're doing, so to convert from the input 3-phase to the single-phase output and then changing the frequency, and just looking at the overall construction, the input is going to the transformer is changing to probably it's obviously 3-phase out of the transformer. I don't know if it's converting to either delta or Y connection, but that output is being rectified. Some very large capacitors here, so if that's converted over to DC, I would imagine that high voltage DC is then being switched, and to me, when you see these 4 transistors right here, this reminds me of an H-bridge configuration, and H-bridge is very common in inverters to switch the high voltage DC and switch that back over to the 60 hertz, and then that would go to the output. So I think that's kind of the basic layout in here, is that they're taking the AC input and converting it over to basically a high voltage DC, and then taking that high voltage DC and switching it at 60 hertz. And then that's, you know, that's just the general path that things are taking. So let's see here. This fan motor right here only has 2 wires going to it, so it says 400 hertz on that capacitor, so it's probably a 400 hertz AC motor, but just single phase, and they're just tapping off on one of the phases to run this fan. If this fan is anything like that Unitron fan, and it does have a similar look to it, it is extremely loud. So when we try and power this up, you're going to hear several different fans running. There's the fan that's in that Unitron power inverter, and it's going to sound like a jet turbine taking off when that thing starts up. There's also going to be fans running in the Hewlett Packard 6269B power supply, which runs the Unitron inverter. So it'll be a little bit noisy around here when we're trying to test this. And then this has a fan in it as well. All right, so let's take a look here on the output. I don't see any other wires right here on that side. Just looking to see where something might go over to this connector in this shield that would be any additional wiring that would be an indication of the output. It's really tight over here. There's no way to see in on this side. Let me take a closer look at things here and see if I can figure out where the output wires are. All right, so I started checking for continuity from other positions of this connector unrelated to the input they were already measured, and then to the rest of the circuit in here. And keep in mind that this hasn't been powered up in years, so there's no danger of capacitors having charge or anything like that in the circuit at this point. But let me show you what I found out. So I just kept the test lead from the ohm meter on the pins that were unrelated, again, to the input that we already checked, and while holding it on one pin, I just probed around in the circuit until I got a reading. And if I go from this center pin right here, there's an orange and a gray wire, and if I touch, orange wire right here, so continuity right there. And if I go to this other pin right here, and I go to the other point right here, it's the gray wire, continuity there. So I believe that those two pins are the output, and if I look right here, I should have letters next to them. Yeah, that's positions B and C. So I think those will be the output. So I couldn't find continuity on any of the other pins in this connector that were unrelated to the the input that we already checked. Those two that appear to be the output, and the others I'm not seeing continuity elsewhere in the circuit. So let's start with those. There'd be more damage, or more risk of damage I should say, if you put power into the wrong pins, and let's say you put voltage in on what should be the output, you would certainly damage something in the circuit. But I'm confident that what we've measured for the input is correct, and if the output is not on the two pins that I was just mentioning, then we can probe around and check if the voltage appears elsewhere. But I think that will be on those two pins. I noticed over here there's a capacitor across those two wires, the orange and the gray wire, and that capacitor says 125 volts and some other ratings on it. It makes sense that that would be across the output for filtering. All right, so what I need to do is put this back together to the point that we can try and power this thing up and see what happens. And I'll make the connections to the inverter for the input, and on the output, I'll put the digital multimeter on there, and we'll monitor for output voltage, and we'll check the frequency, and we can put it on the oscilloscope as well if it comes to life, and we'll see how that output waveform looks. But one thing at a time. Let me put this back together. I'll leave the top cover off when we test it, but I've got to get the circuit board back in place, and let's try and power it up. All right, the circuit board is back in place, and I installed this side panel really just as a matter of precaution because there's some very large high voltage electrolytic capacitors in this corner, and if during testing one of those capacitors were to let go and explode, it'd be nice not to have debris flying everywhere, so this panel adds some protection. Also, where this heatsink assembly attaches to the panel, I freshened up that heatsink compound, but I really don't think anything's going to get all that warm when the inverter is just sitting here with no load on it, and if it does come to life and works, and we can put a light load on it, but I really can't load it all that heavy with these light-duty test leads that I'm using. All right, so let me explain a little bit about the test setup here, and I've got all the test leads connected so we can try and power this thing up. So this box right here is a power distribution box for the Unitron inverter. So this is the 400 hertz three-phase power. And I put that box together many, many years ago when I set up the Unitron inverter on the bench, just as a convenient way to use that inverter, because the inverter's input and output is on a Canon plug similar to this type of a connector right here. Not all that convenient for actually making connections, so something like this is a little bit easier to use, obviously, and the inverter is always up on the bench and ready to go, and this cable right here that is connected to that power distribution box plugs into another box that has the DC power going into the inverter and then the AC power coming out. So it just makes that inverter a little bit easier to use because, again, it just has a Canon plug like this on it. So on this box right here, there's a neon indicator lamp that will turn on when this is active. So you can see the three-phase power coming over here, and then the single-phase output from the frequency converter on these test leads right here. All right, so I'm going to turn on the Hewlett Packard 6269B DC power supply, and you'll hear that fan start up. And then once that's up and running, I'll switch on the Unitron PS65228 inverter. You'll hear that fan come up. It's quite loud. And then we'll try and power this thing up and see what happens. Now, if you are following along and you're working on a device like this, you're definitely doing so at your own risk. Take care and be safe, because there's elevated voltages and you wouldn't want to come in contact with the 115 or the 200 volts. Definitely a lethal voltage at that level. So again, following along, you're definitely doing so at your own risk. All right, so I'm going to walk around over here and turn on the Hewlett Packard power supply. So you can probably hear those fans. And I'm going to increase the voltage up to 28 volts. Okay, that's 28 on the meter. The Unitron inverter likes to have about 27.5 volts. That's its rated input, and there's a little bit of loss in the wiring and the connections between that DC power supply and the inverter, so I always run it at 28 volts, and allows for a slight loss in the wiring. Alright, so this is turned off here, so that's good. So I'll turn on that Unitron inverter, so you'll definitely hear the fan start up on that. Alright, there it goes. It's drawing about 6 amps, so that's normal under no load. The neon indicator lamp is turned on. So I'm going to turn on the digital multimeter. So again, this is not turned on. And let's go over here to AC volts. So if I measure on this power distribution box, my test leads are tangled up here, like that. So if I go from neutral to the 3 phases, so you can see 115 volts, 115, 115, and then of course if you go from phase to phase, the higher voltage. Alright, and if I go over here to menu, and we should be able to go to frequency right here. So you can see it's running at 402 hertz, so essentially 400 hertz, perfectly normal. So no problems there. So I'll go back here to set that back to that, 60 volts. All right, let me connect this to the output, and then we'll be able to monitor right away if there's any voltage coming out. And actually, what I will do is I'm going to put this back on frequency, because this will tell us frequency and voltage, so we can see both at the same time. I should have just left it the way it was, so there we go, that's fine. All right, here we go. Let's see what happens. All right, I'm going to check the power supply over here. It looks good. Just under 10 amps, so no problems there. It doesn't look like this is drawing excessive power. And look at the output, 58 hertz, so just shy of 60 hertz, so no problems there. There's adjustments on this circuit board. I'm sure that frequency could be adjusted. And the output voltage looks good, 115 volts. How cool is that? So it came to life. And it is loud in here with all these fans running, so hopefully the microphone's picking up my voice okay and not getting drowned out by all the fans that are running. But yeah, it seems to be working. So the output voltage is holding steady. Very cool. So let me grab my oscilloscope and hook the oscilloscope to this output, and let's look at the output waveform to see how that looks. Then I can get a small incandescent lamp, and we can put a light load on here just to try it out and see if it, how it handles the load. But yeah, it looks like it's working. So if I go back over to the Hewlett Packard power supply, yeah, it's about 9 amps at 28 volts. So it's perfectly normal. Doesn't look like there's any excessive power being drawn in this frequency converter. Very cool. Well, let me turn this back off. Okay, I'm going to get my oscilloscope, make some connections here, and I'll be back in just a second. All right, I have the Fluke 199C scope meter connected to the output on the frequency converter right here. So let's take a look at the output waveform. Not bad. Look at that. That's a nice looking sine wave. That looks really nice. Oh, I'm really happy to see that. That is a very clean looking sine wave. There's no steps in it, no distortion. Yeah, that looks really good at first glance. No problems there. Definitely a very nicely designed frequency converter. All right, there's a 100-watt incandescent lamp that's connected to the output of the frequency converter. So you can see it's glowing very brightly, and the waveform looks great on the oscilloscope. So it certainly does handle a load. I really can't load it any more than that with these light-duty test leads, but yeah, it seems to be working very well. And if I go around over here to the Hewlett Packard power supply, let's look at the current to run this whole setup. So it looks like about maybe a little over 12 amps. So about 28 volts at 12 amps, maybe 13 amps, right around there. All right, so I'll shut things down, turn this off, and turn the inverter off. And go around here and turn off the HP power supply. Ooh, that's pretty loud with all that's running. Well, very cool. This frequency converter is definitely working, and yeah, it doesn't seem like it needs anything connected to this other small connector that's underneath, which is nice, you know, that it can just basically have power in and get power out. So pretty simple and straightforward to use. So I'll document these connections on here so that I'll know how to hook it up in the future. And I'll see if I can get a Canon plug that plugs into here and make a permanent cable. That would be a nice thing to have. It's all pre-wired and ready to go. All right, so if you enjoyed this video, you can let me know by giving it a thumbs up. And if you're enjoying the content on this channel, don't forget to subscribe, because there'll be many more videos coming up in the near future. So as always, thank you for taking time to watch, and until next time, take care. Goodbye for now.